Hello. This is section 2.4, trigonometric derivatives. So let's think about what is the limit as x approaches 0 of sine of x all over x. What does this equal? Now, we could try to use the squeeze theorem like usual and say the sine of x is range -1 to 1, multiply both sides by 1 over x. And then try to use the squeeze theorem, but the limit as x approaches 0 of -1 over x is -1 over 0, which is undefined. And it's the same thing for positive 1 over 0. They're both undefined. Okay, so the squeeze theorem doesn't work when we try it like this. So we're going to have to get more clever. Okay, so let's do 0. Let's do a parameterization like so. We say that if the sine of x remains within this value, where x is an angle and a real number, that implies that sine of x all over x should be less than 1. All right. And recall, this is for an important note. This is for values of x that range between pi over 2 and 0. So in the first quadrant in the unit circle, right here, first quadrant of the unit circle, there's pi over 2 and here's 0. So x is in between these values right here. All right. Here's our claim that x is less than the tangent of x. Here's our proof of that claim. We have a picture like so. All right. Let's construct our unit circle. Let's create a line here. It comes down. And actually, I want to create a bigger picture so that you guys can see it better. All right. Let's put a line here. We have an angle x. We bring this down to intercept the x-axis and create a right angle. The hypotenuse has value 1 because we're on a unit circle. Let's label this point A, this point O for origin, I'm at B here, this point A. And then we notice that if we extend this line like so, and have it meet up with this line right here, we can reach some point T for tangent. And let's not call this point A. Let's call this the point A. This is some point T. Notice that this ends up equaling tangent of x. Why is that? Well, the tangent of x is equal to the opposite over the hypotenuse leg. Okay, but the opposite legs is this TA. This leg T to A. And the hypotenuse is this OA, but the hypotenuse equals 1 by hypothesis. So that means this is TA over 1, which is just TA. So that means that the tangent of x is purely TA, this line segment TA. Okay, now let's talk about areas of a sector. Notice that the sector OAB area, OAB. So the sector is this wedge of a circle. This is what is in red. This area of the sector, which is equal to 1/2 r squared theta. This is from trigonometry. This is strictly less than the area of the triangle OAT. Notice that this is equal to 1/2 base times height, and that's OA times AT, but OA has unit length, so this becomes a 1. This is 1/2 AT, but AT is tangent of x, so this becomes tangent of x. And for theta is equal to x, the radius is equal to 1. This breaks down to the following equation: 1/2 1 squared, which is just 1, times x, so let's just get an x here, is less than 1/2 tangent of x. We can cancel out the 1/2s to just get x is less than tangent of x. and we're done. That was what we were trying to show, that x is less than tangent of x if x is in between 0 to pi over 2. All right. Let's see what this is getting us. So far, it seems like, why are we doing this? Well, it's because we want to determine what is the limit as x approaches 0 of sine of x all over x. All right. Remember, that's what we wanted to find. And we found that sine of x all over x is less than 1, and that x is less than tangent of x. But notice that tangent of x is sine over cosine. So this means x is less than sine of x over cosine of x. And multiplying both sides by cosine, we get x cosine of x is less than sine of x. All right. And we know sine of x is less than 1. Okay, we knew that from before. So this means we can divide all 3 parts of the inequality by x. So we get cosine is less than sine of x over x, which is less than 1 over x. Aha, now let's try to use the squeeze theorem. Notice that the limit as x approaches 0 of cosine of x is equal to cosine of 0 because it's a continuous function, because it's a trigonometric function. The limit is the same thing as evaluating the function at that point. This becomes 1. Notice that the limit as x approaches wait a second here. I think something went wrong here. Yes, something went wrong here. I need to backtrack. Let's go back to this point right here. I actually said something incorrect. Let's go back to this point. The x is less than tangent of x. That implies x is less than sine of x over cosine of x. Multiply both sides by cosine, so we get x cosine of x is less than sine of x. All right. So what we can now do is actually say, oh, that implies cosine of x is less than sine of x all over x. That is what is actually less than 1. Sine of x was not necessarily less than 1. But we know that sine of x over x is less than 1. We'd said that before over here. So that was my error that we made there. But we fixed that error. Now we can move on. Now let's try the squeeze theorem. The limit as x approaches 0 of cosine of x is evaluating the function at that value because it's continuous, but that equals 1. And the limit of a constant is just a constant itself. So these two limits agree, and that means by the squeeze theorem, that implies the limit as x approaches 0 of sine of x all over x is equal to 1. This is quite counterintuitive because this is a ratio of continuous functions, right? Well, 0 is not in the domain of this ratio, this rational function, because when we plug in a 0, we get sine of 0 over 0, but that's 0 over 0, and that's undefined. But when we take the limit, if we infinitely approach it but don't touch it, it ends up equaling this defined value of 1. So it's very, very interesting. Okay. So now let's talk about the transfer principle. Again, let's discuss the transfer principle. In application to sine of x over x is less than 1, the transfer principle states that that implies sine of alpha over alpha should be less than 1. Okay. And matter of fact, because the limit as x approaches 0, the sine of x all over x is equal to 1, that means sine of alpha all over alpha, so we should say less than or equal to, it ends up equaling 1 because alpha is basically 0. So when we plug in here at alpha, it's basically going to produce the limit value. So we could say this approximates to 1. It's a very good approximation. Or we could say that it renders to 1. Either way. So notice that when we multiply both sides by an alpha, this implies that sine of alpha is approximately alpha. So this is called the sine approximation. So let's use the sine approximation. What is the limit as x approaches 0, a sine of 3x divided by 7x? Okay, this is equal to sine of 3 times alpha plus 0 all over 7 times alpha plus 0. This becomes sine of 3 alpha over 7 alpha. Notice that by the approximation, this becomes a 3 alpha over 7 alpha. Alphas cancel, so our final answer is 3 over 7. The sine approximation formula allows for pretty quick calculations like that with regards to limits of sine. Now we're going to come up with a cosine approximation formula, and it's going to say cosine of alpha is approximately 1. Why is that? Well, because the cosine of alpha is equal to the limit as x approaches 0 cosine of x. That's equal to cosine of x of 0 plus some alpha. But that's equal to the cosine of alpha. But notice that's also approximately equal to cosine of 0. But that is strictly equal to 1. So that's why we get cosine of alpha is approximately 1. Because this approximate sign is attached to a chain in which the other side of the chain is equal to a cosine of alpha. So this is our cosine approximation. This was our sine approximation. Here's our cosine approximation. So let's do some limits here. What is the limit as theta approaches 0 of theta cotangent of 3 theta? Okay. Notice that if we just plug in a 0, we get an undefined. We get 0 times cosine of 0 divided by sine of 0. That's 0 times 1 over 0. That's undefined. So notice that the limit as theta approaches 0 of theta cotangent of 3 theta is the same thing as the limit as theta approaches 0 of theta times cosine of 3 theta over sine of 3 theta. And that's the same thing as 0 plus alpha, which we'll just write alpha, of cosine of 3 times 0 plus alpha, which we'll just write 3 alpha, all over sine of 0 plus alpha times 3, which is just 3 alpha. This ends up equaling, and we got an alpha out here, cosine of 3 alpha approximates to 1. Because 3 alpha is basically 0. Sine of 3 alpha approximates to just 3 alpha. Notice then we get alpha over 3 alpha. Alphas cancel, so we get 1/3. Amazing. We were able to extract a finite value out of this limit as theta approaches 0. When we brute force plug in a 0, we don't get anything meaningful. But by thinking about it in terms of infinitesimals, we do get something finite and something meaningful, which is incredible. All right. Let's talk about the limit as x approaches 0 of sine of 5x all over sine of 7x. This is equal to sine of 5 alpha over sine of 7 alpha. But by the approximation principle, this is just 5 alpha over 7 alpha. Cancel out the alphas, and we get this. So as you can see, this is a pretty handy-dandy approximation technique. All right. So now let's take a look at this. This is a theorem that the limit as x approaches 0 of cosine of x minus 1 divided by x is equal to 0. let's prove this. The limit as x approaches 0 of cosine of x minus 1 all over x. This is the same thing as cosine of alpha minus 1 divided by alpha. Okay. But notice that by the approximation principle, cosine of alpha is basically cosine of 0, and that's just 1. So we get 1 minus 1 all over alpha, but then we get 0 over alpha, which equals 0. This violates the approximation principle. So we can't do that. We can do something that allows us to get away with this without doing the violation of the approximation principle. So let's forget the limit part. Let's just say cosine of alpha minus 1 all over alpha. And let's multiply top and bottom by the conjugate. Cosine of alpha plus 1, cosine of alpha plus 1. This ends up giving us cosine squared alpha minus 1 all over alpha times the quantity cosine of alpha plus 1. Notice that sine squared alpha plus cosine squared alpha is equal to 1. This is the Pythagorean identity. And so this implies that cosine squared alpha minus 1 is equal to negative sine squared alpha. So this can be replaced with negative sine squared alpha all over alpha times the quantity cosine of alpha plus 1. So then negative sine squared alpha is just negative sine of alpha times itself, right? Okay, so utilizing the approximation principle, that's just a negative alpha times a negative alpha. Because negative, we'll just put the negative out here. That's sine of alpha times sine of alpha. But sine of alpha approximates to an alpha, so we just get a negative alpha times alpha over here. And this is alpha times cosine of alpha approximates to 1. So we get a 1 plus 1 down here. So then we can cancel out one of the alphas, so we get a negative alpha all over a 2. And notice that this renders the real result 0. And hence, that's why we stated that that limit is equal to 0. So let's recall the sum of angle identities. Sine of A plus B is equal to sine of A, cosine of B, plus cosine of A, sine of B. And that the cosine of A plus B is equal to cosine of A, cosine of B minus sine A, sine B. Now let's discuss what is the derivative of sine of x. Recall, by definition, this is sine of alpha plus x minus sine of x all over alpha. But utilizing the sum of angles identity, we'll get sine of alpha cosine of x plus cosine of alpha sine of x minus sine of x all over alpha. Notice then we can use approximation. Sine of alpha is just an alpha. Cosine of alpha is basically cosine of 0, which is just a 1. Sine of x is canceled, so we get alpha cosine of x all over alpha. Cancel out the alpha, so we get cosine of x. Aha! This implies that the derivative of sine of x is cosine of x. Very cool. So what is the derivative of cosine of x? Well, that's equal to the cosine of x plus alpha minus cosine of x all over alpha. And we can use the cosine sum of angles formula. So this becomes cosine of x cosine of alpha minus sine of x, sine of alpha, minus this cosine of x, all over alpha. And then we can use our approximations. So cosine of alpha is just a 1. Sine of alpha is just an alpha. Cosines cancel. So just get a negative sine of x alpha divided by alpha. And the alphas can cancel, so we get negative sine of x. Aha! So the derivative of cosine of x is negative sine of x. Cool, huh? So now, what is the derivative of tangent of x? Well, that's the d dx of sine of x over cosine of x. Recall the quotient rule says bottom times derivative of the top minus top times derivative of the bottom all over the bottom squared. Derivative of sine is cosine, so we get cosine squared x here. Minus the derivative of cosine is negative sine, so this becomes sine of x times negative sine of x all over cosine squared x. So then this reduces to cosine squared x plus sine squared x all over cosine squared x. The top is equal to 1 by the Pythagorean identity. Cosine squared x plus sine squared x is equal to 1. And 1 over cosine squared x is the same thing as secant squared x. Aha! So that implies d dx of tangent of x is equal to secant squared x. Let's do another example. What is the d dx of secant of x, for example? That's d dx of 1 over cosine of x. So the derivative of the quotient rule says bottom times the derivative of top minus top times the derivative of the bottom all over the bottom squared. So this reduces to a 0 minus derivative of cosine is negative sine all over cosine squared x. So the negatives cancel to get sine of x over cosine squared x. But this is the same thing as sine of x over cosine of x times 1 over cosine of x, right? But that's the same thing as tangent of x, secant of x. And that's what your d dx of secant of x is. All right. Here's another example. What if our f of x is a product of two functions, x times sine of x? What is f prime of x? Well, f prime of x is equal to d dx of these guys. It's a product of two functions. So we get x prime sine of x plus sine of x prime x. So this becomes 1 times sine of x. Derivative of sine is cosine. So this reduces to sine of x plus x cosine of x. Let's do another one. What if our function is equal to something more robust? What if y of x is equal to x squared tangent of x divided by 3x minus 7? What is y prime of x? Well, y prime of x is equal to the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Okay, so this ends up becoming 3x minus 7 times, now this is a product of two functions, right? X squared times tangent of x. So now we have to do the product rule for them. So then this breaks down to something even further. This becomes x squared prime tangent of x plus tangent of x prime x squared minus this thing reduces to just the 3 times x squared tangent of x. everything divided by 3x minus 7 quantity squared. So then this reduces to a 3x minus 7 times 2x tangent of x plus, recall what the derivative of tangent of x was. If you go back in time and we look in our notes, the derivative of tangent of x is secant squared x. So this becomes x squared secant squared x. Close the parentheses, minus the 3x squared tangent of x, everything divided by 3x minus 7 quantity squared. This is what the derivative is. This takes practice, guys. You guys have to do a lot of practice to understand how to do this stuff. Make sure you do it over and over again until you are repeatedly getting the right results. Make sure to pay attention to minus signs and make sure that your arithmetic is correct. So what is d squared y dx squared if y is equal to secant of x? Well, notice that d squared y dx squared is the same thing as d dx of d dx of y. So that's d dx of d dx of secant of x. And we've done what the derivative of secant of x is. d dx of secant of x right here is tangent x secant of x. Now we got to take the derivative of tangent x secant of x. Notice that's tangent of x prime secant of x plus secant of x prime tangent of x. The derivative of tangent of x is secant x tangent x. Oh, no. The derivative of tangent x is secant squared x. The derivative of secant of x is tangent squared secant of x. The derivative of secant of x is equal to tangent x secant x. That's what I mean to say. So this reduces to secant cube x plus tangent squared x secant x. Okay, so I'm trying to fly through this really quickly, and yeah, make sure you guys take your time. Okay, let's do another example. What is the derivative of this? Well, it's the bottom times derivative of the top minus the top times derivative of the bottom all over the bottom quantity squared. The derivative of sine is cosine. And the derivative of this guy is 1. Derivative of x is 1. Derivative of cosine is negative sine. All right, so then we're done. You can just stop right there. Now let's talk about what's so cool about trigonometric derivatives, besides the fact that they correlate to geometry. What else are they useful for? Well, they have applications in theoretical physics and in engineering. Here's an application example. It correlates to simple harmonic motion. Simple harmonic motion is like a repeating motion, a motion that repeats, like my hand. My hand is going through simple harmonic motion. It's moving through a defined, like let's say here's the page. I'm going through simple harmonic motion. I'm just repetitively going back and forth, staying within the same range. Objects that exhibit this pattern of motion are said to exhibit simple harmonic motion. And we find this kind of pattern in nature very often. You can think of it as like a pendulum swinging. You could think of it as a water wave propagating through a lake. You could think of it as a, let's say you have a spring attached to a mass, M. Okay. At some point in time, it's at some value here, but as you move forward in time, this is if you hold it up there with your hand, right? If you let go of your hand, then the spring is going to fall down because that mass is going to pull it down. And so now it's going to have some displacement. Okay. So let's say we want to model this situation mathematically. Well, we can measure how much displacement this has. For example, what if it's 5 meters? Okay, then we can say, okay, after some time when you move forward, what if the mass then, because it's a spring, as it falls down, it's going to go back up, right? Because that's what springs do. So then you get this happening. Now, it's 5 meters above where it was originally. So here it is at rest, and we have our hand there, and we let it go. It drops, but then the spring pulls it back up. Okay. So how do we model this kind of behavior? Well, we could say that the position function with respect to time, P of t, of the mass is equal to 5 cosine of t. All right. Let's see what we mean by this. All right, let's plug in various values for t. Well, P of 0 is equal to 5 cosine of 0, but that's 5 times 1, which is 5. P of, let's say, pi over 2 is equal to 5 cosine of pi over 2, but that's 5 times 0, which is 0. P of pi is equal to 5 cosine of pi, but that's 5 times the negative 1, and that's negative 5. P of, let's say, 3 pi over 2 is the same thing as 5 cosine of 3 pi over 2, but that's 5 times 0, which is just 0. P of 2 pi is basically 5 cosine of 2 pi, but that's 5 times 1, which is equal to 5. Notice that these values are oscillating, and they represent simple harmonic motion, where here it's going up, back down to the original spot, down, then going back to the original spot, then up. So you can kind of see it as like a t equals 0. Here's our mass. This is a displacement of positive 5 meters up. And then at t equals pi over 2, it's now at the value of 0. Then at t equals pi, it's dipped 5 meters below that original value. And at t equals 3 pi over 2, it goes back to the original value. Then at t equals 2 pi, for example, now it's above the original spot by 5 meters. Notice this would be negative 5 meters because it's below the original spot. This is positive 5 meters because it's above the original spot. So notice that using a trigonometric function could allow us to model a mass on a spring. Well, who cares about a mass on a spring? You know, what's so important about this? Well, This is very important. Matter of fact, a mass on a spring is what your car is. Your car is a mass on 4 springs. Your 4 wheels have shocks. Those shocks are springs. So if you invert this situation and you think of the masses as tires on a road, then this tire is on the road and, oh, actually, let me not flip it. Let's say the mass is the tire. It's attached to the springs. So while you're driving your car and you get in your car, the spring gets compressed because you weighed some weight. And let's say you drive over a hill and the weight goes up. You go beyond, the shock expands. So this kind of mathematics has a lot of applications in engineering and in real life situations, especially when you talk about what is the force of a spring. It's a Hooke's law. The force is equal to negative k delta x, or delta y in this case.